The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
What is the research, why we're looking at it, what are the problems we're investigating, kind of where we're going with it. So, kind of get started, a little bit about the roadblocks for implementing high-strength reinforcing bars currently. We have some material issues, Jacob touched on some of them. We have stress-strain behavior, we have fatigue behavior, we have production repeatability issues. We also have a lot of structural issues, stiffness, strength compatibility, bar demands, detailing, and such. I'll give you a little overview of each, just kind of give us a flavor of what we're talking about, starting with some material issues. Currently in the US we have maybe 3 main ways we're producing high-strength reinforcing bars, and that's really a broad generalization. We have the MMFX steel, where that has that roundhouse stress-strain curve. We have microalloying, it has a bit of a yield plateau and a good hardening shape. We have quenching and tempering, that's very similar. And all these compared this way to grade 60, obviously there is some compromise there from grade 60 to here. If we look at the stress-strain behavior in a little more detail, so fracture elongation is something we do compromise, as Jacob mentioned, and that is something that may be of concern for seismic applications. If we look at the yield plateau, we have it or we don't. So looking at what are the effects behaviorally of this shape of the stress-strain curve here. We also have the hardening behavior. So if we look at, if we normalize the yield by the yield strength, 1 here being the yield strength, we see some have a certain hardening ratio. Grade 60 is way up there in this hardening ratio, so that hardening ratio will affect quite a few behavioral items. And other issues, well, what about fatigue? It's very nice if we get a beautiful stress-strain curve and the metallurgists give us grade 100 that goes to 30% elongation and we're all happy with it, but then you cycle it once and it fractures on you. And so we want to look at other things about fatigue, and really we should also try and figure out what is that happy compromise that Jacob was talking about, where do we go from there. So on this structural side of things, I made a laundry list. I don't expect you to read it all. Of things, we have higher strain at yield, which means larger cracks, larger deflections. Higher strength means larger tensile forces, longer development length, longer splice length, anchorage issues, larger compression forces, bigger buckling propensity for those bars given a certain lateral bracing, less ductility for seismic members, tensile to yield ratio issues with plasticity spreads, strain concentrations, and possibly leading to premature fracture. So there's a wide range of structural issues to deal with, and I'm going to kind of touch a little bit on a lot of these as I go through reviewing some research. Now, where we started about 4 or 5 years ago now is what I call the cycle of inaction. I think Jacob mentioned a little bit of that. The design standard did not allow or don't allow high-strength reinforcing bars. Therefore, the engineers don't specify the high-strength reinforcing bars. Therefore, the mills don't produce the high-strength reinforcing bars. Therefore, the researchers can access high-strength reinforcing bars to perform research on them. And we're back to where we started, no research, no design standard, and we get stuck in this cycle of inaction. So, and at the same time, engineers are pushing for it, there's a demand for it, and they go to the mills and say, well, give us the steel, and the mills say, well, what do you want? Do you want more elongation? Do you want more T2I? Do you want this? Do you want that? And we really don't have an idea. So when all this got started, we were still trying to figure out, well, what are those properties that are acceptable? What should the mills target to get us started? Let's start with some steel that we agree on is where we want to end up roughly, and go with there. So where it started off with some targeted material and structural testing that I'll talk about and kind of see where it led us. Looking at material testing, so this was completed about a couple of years ago. So we looked at the low cycle fatigue performance of these bars. Now, the montonic properties were covered by the mills. They were all doing a lot of tension tests, and I think Conrad Paulsen did a lot of statistics on those. We were interested in the fatigue behavior of the bars. We tested a bunch of things, different grades, different sizes, different manufacturing processes, different clear spans to adjust for buckling, and different loading protocols on these bars. And so here's a bar being tested, plus and minus 2% strain. At 6 dB clear span between the grips. And we kind of see what happens to it. It starts to buckle a little bit. You start seeing some strain concentrations right at the bar deformations. And eventually that bar cycles a few times and will fracture. So that behavior is what we're looking at, trying to figure out, well, what are the differences between the different manufacturing processes, how it affects this, and what are the numbers that we would like. I mean, that particular project, we're just trying to benchmark grade 80, 100 versus grade 60. So where do we stand with respect to our gold standard of grade 60? And here's the fracture right there of the bar. So summary of findings from that study is, well, the good news was that the grade 100 bars we tested had about 90% of the cycles to failure of the grade 60 bars we tested, which was really good news. So they're fairly equivalent. However, the not so good news at that point was that there was a very large variability in the grade 100 performance. We had worse performance for larger bars, we had a very variable performance at lower clear spans, and we saw significant differences in the manufacturing process where we had some failure modes that were very different. Now, if you compare some results from one of these tests, this is the clear span the bars were tested at, 4 dB, 5 dB, 6 dB. Number of half cycles to failure. If you look at the grade 60, that's the light blue color here, you'll see maybe about 45, 47 half cycles to fracture here at 5 dB, at 6 dB. As you'd expect, it goes down as you get more and more buckling. Now you look at the grade 100, which is a dark color here, and you find that it matched reasonably well with the grade 60 here, shot off right there at 4 dB. But I think what I found the more interesting part is if you look at the error bars for the test, so we put on the error bars. For the grade 60, the error bars are right here and right there. You can barely see them here and you can barely see them there. The error bars for the grade 100 bars were from here to there, and from here to there, and from here to here. So very big variability in the numbers. And what came in as a surprise is that the grade 80 was very variable. Some came in much higher, some came in much lower than grade 60. And so the grade 80 conclusion was some much lower, some much higher, but we've only tested a few at that point. So that started us thinking, well, we should really try and figure out how to refine those grades. So we went and put those bars in some column tests to look at what happened to them and how they actually behave in a few column tests. We did a series 1 with shear and confinement was what we're looking at, and series 2 looking at plasticity spread. The steel in series 1, grade 60, 80, 100. This is the longitudinal bars, transverse bars. If you look at 60 and 80, this is the hysteretic behavior we found. Almost identical, really on top of each other, which was really great news. So almost identical behavior, both of them stable to about 5.5% drift, which was really good news. So overall, very good performance. And these were intended to fail in shear, and they did so at 5% drift or 5.5% drift, shear and axial failure at the end of the tests. So pretty good response, grade 60, grade 80 equivalent, we were happy with that. Grade 100 failed by anchorage, even though those were identically, well, nominally identical designs. We had 12 grade 60 number 10 bars, 12 number 9 grade 80 bars, and 12 number 8 grade 100 bars, equal strength. This one failed by anchorage failure along the length of the column. So this highlights that higher strength bars need drive bigger bond forces, and there's currently a ballot in progress in 318 about this topic. Now what we also noticed that was interesting in these tests was that the strain demands on the bars were different. So at any given drift ratio, let's say 1%, 1.5%, and as we go forward, this is before the grade 100 column sustained a anchorage failure. We see that the grade 60 strains are here, and those bars at the ends. Grade 80, grade 100. Very different strain demands on the bars, same mostly the same design. And so these numbers were quite different, which got us thinking. And if we looked at the material testing we did, and this is total strain range, so this is strain range to which you cycle a bar versus half cycles to failure. This is from the material testing part. If you increased your strain amplitude by 100%, you decrease the cycles to fracture by an order of magnitude. So we looked at this and said, well, maybe we should look in a little bit more at this performance. Maybe high-strength reinforcing bars need better fatigue performance than grade 60 bars. Don't worry, it gets better than this. So at that point, we kind of paused and said, hey, something's up. So we looked at Series 2. So the intent of Series 2 was to investigate three main types, as I mentioned, kind of the low hardening, high hardening, and kind of the MMFX shape, and looking at maximizing the strain demands in the bars, getting bar fractures to occur in those specimens so that we can see, is that materializing in the columns themselves. And so these are 4 columns, a grade 60 benchmark and 3 grade 100s. T2Y of 1.27, 1.16, and 1.27 here. And this is kind of the basic design. So we adjusted the hoop spacing according to what we think is going to land in the next in 318. But other than that, everything was identical. Everything had number 6 bars, everything just fairly similar, except the hoop spacing is what we changed between these columns, same axial loads, same concrete strength. This is the steel, so these are the 4 steels we looked at. And here's the behavior of these 4 columns. If we look at, let's see, this is the grade 61, this is the MMFX one, I believe, high T2Y, low T2Y. You can see that they're roughly equivalent. They all got up to about 5%, 5.5% drift, so everything was fine. And then the red here indicates fracture of bars. So we start fracturing bars here, fracturing bars there, here and there, and here and there. So they all failed by bar fractures. They all went to 5.5% drift, so we're very happy. So all the grade 100s that we looked at did reasonably well, and I think very well actually. We looked at the failure mode, the bar fractures. There were some differences observed in behavior. I don't want to get into the details here. Just kind of highlight, we saw differences in the behaviors, even though the end result was about the same for these tests. Can't see this very much. And then we plotted those strains in the bar normalized by the section depth versus drift ratio. And we put this first series columns on it. These are the 4 columns and some other columns we got from the literature. And what we found is, let's say you take 2% drift ratio, you can have strain demands down here or up here. Very, very different. Now you can say, okay, well, these are 2 very different columns, different axial loads and different things. These are the 4 columns that were pretty much identically designed, just different bar properties. And you can see here quite a big difference at any given drift ratio and the strain demands in the bars. So it's a complex behavior. We started looking at it, trying to figure out, well, why are some doing worse than others or better, and what is driving all of this in the behavior. Now, Series 2 conclusions, overall similar and good seismic behavior for all the columns. We looked at the strain demands, and they have a lot of variables that are affecting them. And then we got to the point of asking ourselves, well, okay, well, there's big differences here and there, but what is really an acceptable number? What is an acceptable fatigue performance of these bars? What do they need to sustain to give us the same safety margins in our members, in our structures? And that is a follow-up project that I'll talk a little bit about that we just started. Now, I must mention there's a complementary beam project at UC Berkeley that's looking at this. So this was done in conjunction with UC Berkeley. Highlight this. This is by Dewey Toe, Nick Hartsey, and Jack Maley at Berkeley, looking at very similar beam. So they did the beam equivalent to what we did in Texas. This is what their beam tests look like, and these are their results. So overall, when you look at the different T2Y ratios, different types of steels, not too bad. There was a problem with this test, so I would discard it. They had some welding issues that I wouldn't count on this one, but these tests here, fairly equivalent, not too bad in the beams also. Now, the current project we just started is, well, what do we do with all this? Now, where do we go with all this, and what do we do with it? And here is trying to define what is acceptable elongation. So what do we put in the STM spec for those bars as acceptable elongation? What is acceptable low cycle fatigue behavior of those bars? I mean, this high is low, but how low can you go, or how low can you accept to go, or how high does it need to be? You can think about it both ways. So this is just started late 2016. The tasks for this project are fourfold. We're looking at quantifying the fatigue performance of all the bars, the mills, the productions in the US, the main ones at least. In the previous study, we only tested 2 manufacturing processes, so we're expanding it. We're also, with an associated project, we're looking at improving that behavior with some mills, so we're working with some mills to improve their behavior. From there, we're looking at developing a model for predicting bar fractures. So from there, we have the bar performance, we have the member performance, we're putting it all together, trying to get what is the effect on the member performance, and when can we expect fracture of these bars in sections, walls, beams, coupling beams. Then is to quantify the differences in probability of collapse of seismically detailed buildings. So are all these changing our probability of collapse of those buildings? How much so, and what can we do to help it out? And the final part of this is recommend any design changes and ASTM specifications to get us to whatever those probability of collapse ACI 318 are and deem useful. So that's this project. This part of it is in collaboration with Stanford, so they're doing a lot of the analytical work, looking at the building performance and the collapse hazards. This is from their work, Quan Shi and Professor Dearline, looking at the bar behavior, then looking at, these are the tests from Berkeley. If you look at the grade 60 and the grade 100 bars with the low T2I, you see there's some differences. What are those differences, and how do they translate into differences at the global structural level? And these studies will help us really determine, okay, well, what are the differences, and what should we do to either improve them, or can we live with whatever those differences are? Now, from here on in, so this is looking at really trying to define what are the next bar, what is that ASTM spec, what are those bars and those properties that we'll be very happy with. But while the steel bar production and ASTM specifications are being finalized, so the manufacturers and the mills are improving their steel, we're looking at ways to control things in the ASTM spec to clean up that steel a little bit so we don't have that huge variability, things like that. There's a broader research going on, and I'll touch a little bit on some key points of that research, especially those that are in debate in 318. So the Charles Pankow Foundation commissioned the study about a couple of years ago now, looking at a roadmap for high-strength reinforcing. So what is all the research that we need to do to get all that steel into our codes? They estimated in that study about $26 million of research that should be done. And so we're getting kind of started in it. First things first, get the steel you want with the ASM spec, then do the bulk of this work. But we can get started. We have steel that seems to be promising and working out for us. And nothing like this number to bring the research community together. We are all working very hard to spend that money, I assure you. And I'll touch on a few topics of interest, looking at some bar bends. The steel is more brittle, so it needs maybe a wider bends, gravity beams, shear walls, anchorage and bond and coupling beams just started, so I don't have much on these, but I'm going to highlight a bit of research that's being done. So performance of bends, looking at how those bends are and what are the bend diameters. I'm not going to get into the details of this one. This is a study that was completed last year. We looked at also kind of the main 4 with ways of doing 3 ways, but 2 multiple different manufacturers to kind of get a full sampling. And this resulted in recommendations for new bar diameters, not very different from what we have currently in ACI, based depending on whether you look at a yield stress performance objective or you just try to match whatever grade 60 is what we're happy with. It gives us these numbers here. So we're looking at this. The discussion started in 318R, but then we started thinking about things, well, what about cold weather performance? And so the discussion's ongoing. New project just started in January, looking at cold weather bending, cold weather performance of those bends. And we're hoping towards the end of 2017 to revisit the bar bending and look at it kind of across warm weather, cold weather, and try and figure out what those new bar bends are. Likely not big changes, but maybe, 1 bar diameter more or something along those lines. We'll see where that lands at the end of it. In terms of gravity beams, a couple of studies I want to highlight. One is at Berkeley by Nick Hardesty and Jack Maley. They're looking at, what is the allowable maximum reinforcement for steel, for high-strength reinforced bars, or minimum? So beams that are very lightly reinforced or beams that are very highly reinforced. If you recognize, this is the 5-factor table chart in ACI 318. What should those limits be for high-strength reinforcing bars? So they tested lightly reinforced beams, looking at what those numbers should be. So looking at kind of the general behavior, stiffness differences, but mainly looking at that ductility, see what those, if that is acceptable in those region. The other extreme is heavily reinforced, so how much is too much steel in a section if they're high-strength reinforcing bars. So similar type of setup, but now we have a lot of steel in those sections. This is kind of failure mode with a bit of crushing at the top, at the end of it. Another study looking at gravity beams, this is in Purdue. They're looking also at what about moment redistribution. Those bars are less ductile, they have different behavior. Can we allow moment redistribution across big spans? So they looked at this. This is kind of a continuous beam tested there. Got grade 60 and grade 120 bars and different reinforcement. And they're looking also at what can we redistribute moments. What is the ductility of these things? You'll see the grade 60 behavior is here, the grade 120 is here. Notice some stiffness changes. They ran out of stroke, I believe, here, but it's still a pretty decent deformation range, indicating that these bars can work really well in those settings. On the wall side, Andres Lepage, Remy Lequen up in Kansas, looking at walls. Now, the interesting thing about walls is they will develop high strain demands. Because the sections are so big, you are going to get big strain demands on those bars. And so that was an interesting project looking at this. This is sponsored by Pankow Foundation, supported by CRSI members and CRSI and the advisory panel on that project. They also looked at kind of the equivalent of what the columns and the beams did, but for the walls. So same thing, kind of 4 walls. T2Y is different. We have a moderate T2Y in the grade 60, T21, which came in about 1.34 T2Y. T2 is a very low T2Y at 114. Then there's a moderate T2Y, and then there's a high T2Y, and one of these is that kind of roundhouse shape. These are the walls up in Kansas. Looking at these, the tests have been completed. And this is kind of the reinforcement details. I'm not going to get into the details of it, just a quick summary of the results. If you compare T1 to T3, T3 has a moderate T2I ratio, 1.23. You notice the behavior is not terribly different. Some differences in stiffness and things like that. Bar started fracture here, bar started fracture here in the grade 60. Equivalent performance, not too bad. This one performed rather poorly, in my opinion. This is the grade 60 benchmark, this is the grade 100. This is the one that has really low T2Y and also has really low elongations on the transverse bar, as I believe. And this test highlighted that we need to really pay attention to our bar detailing. We can get, if we look up here, very good performance, or we can get poor performance. And so we really have to iron out those details. But good performance is possible. Here's T4 with the 1.38 to I ratio, very good performance. So good performance is possible. We can do it. We just have to make sure we do it right. And this kind of pictures of those things. As I mentioned, the T2 had a low T2I, low elongations and transverse bars. Deformations were kind of sharp on this one. So there's a lot of things that we can improve and have been, some of them have been improved since then. But the good news about all this is it can be done, and we've seen very good performance with grade 100. In conclusions, this is the broad conclusion, take-home message for you tonight. Overall, very good behavior of concrete members with high-strength reinforcing bars. We've seen it in beams, we've seen it in columns, we've seen it in walls. We can get good performance. Some concerns have highlighted some detailing issues that we need to iron out. We need to iron out acceptable bar properties and make sure that the production is reliable and repeatable. And in the end, in my humble opinion, I think high-strength reinforcing bars will be the future. I think they've shown that they can do the job and well. We had similar concerns back in the 60s when we moved from grade 40 to 60, and I think we're well on our way to resolving those concerns for the new batch. And of course, we'd like to thank all involved, especially the CRSI members that have donated a lot of steel and sweat and blood into this one. Thank you all.